Today we're going to look at some applications of derivatives for our inverse trig functions. We'll take a look at a couple of writing equations of tangent lines and one finding extrema and inflection points. Starting off with our tangent line, in order to write the equation for the tangent line, we need the slope. In order to find the slope, we need the derivative. So take a moment and think about what the derivative of the arctan function is. The derivative of arctan is u prime, so the derivative of what's inside, over 1 plus u squared. So in our case, the derivative of x over 2 is 1/2. I'm just going to multiply that by our derivative. So we'll have 1 over 1 plus that x over 2 squared, which will give us x squared over 2 squared, which is 4. Now, because we just need the slope, we don't have to clean this up. I'm going to sub in my x value for x and simplify to get my slope. So we'll still have that 1/2 being multiplied by 1 over 1 plus 2 squared, which is 4 over 4. Simplifying that, we've got our 1/2 times 1 over 1 plus 1, that 4 over 4 simplifies. So we really have 1/2 times 1/2, which gives us 1/4. There's our slope. We were given a point to begin with. So our equation will be y equals 1/4 times the quantity x minus 2, that x value for our point, plus pi over 4, the y value for our point. Second one, we've got some implicit differentiation with this tangent line. We've got arcsine of x plus arcsine of y. So take a moment to think about what the derivative of our arcsine function is. And that one is 1 over, in this case we have no chain rule because we have regular plain old x, square root of 1 minus x squared. So that'll be the same derivative for our arcsine of y function, except we will have a chain rule this time because the derivative of y is dy dx. And the derivative of pi over 2 is 0. And again, the nice thing for this one is we don't have to clean it up because we are given a point. So I'm going to take this point and sub those values in for x and y right away. And then I'm going to be solving for dy dx in terms of a number because that'll be our slope instead of with a variable. So hopefully that will make our lives a little bit easier. Starting by subbing in that square root of 2 over square root of 2 for x. Subbing that same value in for y. So now we need to simplify these expressions. First thing I want to do is square that square root of 2 over 2. So the square root of 2 squared is 2, and the square root of 2 is 4. So we're going to have 2 over 4, or 1/2. So 1 minus 1/2 in both of our denominators. So here's what I notice. I've got that same coefficient in front of my dy dx as I'm adding to it. So when I subtract that expression from both sides to start to get dy dx alone, I'm going to end up dividing something by itself, except for the one I subtracted will be negative. So I don't have to go any further in trying to simplify this expression by subtracting 1/2 from 1 or taking the square root or rationalizing any denominators. I am going to get something divided by itself is 1, except like I mentioned, it's negative on the one side. So our slope is -1. If you want to double check my work, feel free to go ahead and push this into your calculator with all of the radicals and fractions within it, and you should get a slope of -1 as well. So now we have our slope of -1, and our point was √2 over 2, √2 over 2 for both the x and the y value. So the equation of my tangent line will be -1 times x minus √2 over 2 for that x value, plus the y value was again √2 over 2. All right, this last one we're going to be taking a look at arc cosine, and we're going to find any relative extrema as well as any inflection points. We're going to use the derivative to find the relative extrema first. So take a moment and think about what the derivative of arc cosine is. The derivative of our arc cosine function is almost exactly the same as that arc sine function. It will be a negative in the numerator. So first I'll multiply by the derivative of what's inside. That u prime would go in the numerator, but since my u prime is a fraction, I'm going to multiply that out front so I don't end up with a complex fraction. And then we'll have -1 over the square root of 1 minus what we're taking the arc cosine of, which is that x over 4 quantity squared. Now, unlike before, where I was able to sub in some values and I didn't need to simplify, this one we're looking for critical values. So we're going to set it equal to 0. When I set this expression equal to 0, the first thing I notice is I could multiply both sides by 4 to cancel that multiplication by 1/4. I can also cancel that negative in the numerator by dividing both sides by a negative. It's still 0. So really I'm setting 1 over 1 minus, and I'm going to simplify that inside function, x squared over 16 equal to 0. Now, in order for this to equal 0, the numerator has to equal 0. Think about multiplying both sides by that denominator to cancel it. So I get 0 equals 1. Well, of course, that's not true, so this has no critical values. Therefore, there are no relative extrema for this function. All right, so in order to find any inflection points, I will need the second derivative. So what I want to do to take the second derivative of this is simplify it a little bit. I notice that I have this expression in the denominator that's being square rooted. If I bring that to the numerator, that will be a -1/2 power. So I have 1/4 times the quantity 1 minus, I'm going to simplify that again, x squared over 16 to the -1/2 power. And then the derivative of arc cosine is negative, so I'm going to multiply that negative by the 1/4 as well. One more thing I want to do to clean this up before I take the derivative is make that 1/16 a coefficient for my x squared so that I don't have that fraction inside. Now I'm going to go ahead and take the derivative of this function. Second derivative helps us find those points of inflection. So this is power rule. I'm going to take that -1/2 and multiply it by my -1/4 to get a positive 1/8. Keep the inside function the same. Subtract 1 from the power. And then multiply by the derivative of what's inside. So the derivative of 1 is 0, and the derivative of -1/16 x squared. Multiply that coefficient by the power, so 2 times 1/16 gives me a 1/8, and it was negative, and then subtract 1 from the exponent. Cleaning this up a little bit, I have this x in the numerator. I'm going to keep the negative with the x. 8 times 8 will go in the denominator. as well as this entire expression that's being raised to a negative exponent. And of course, the exponent becomes positive when it moves to the denominator. Same thing, we need to find the critical values of this function, setting it equal to 0. If I multiply both sides by that denominator, the entire denominator goes away. I can divide that numerator by -1, and I get a critical value of x equals 0 when I'm looking for the inflection points for this function. Our second derivative test, using that as a critical value, that denominator will always be positive. I'm taking the x value and squaring it, and I'm raising to a 3/2 power, all positive. Multiplying by 64 is positive. So if I take a number smaller than 0 and put it into that numerator, multiplying by -1 will make that positive. Multiplying a positive by the -1 will make it negative. So we do have a change in sign, which gives us that inflection point. In order to actually find the inflection point, we have one more step. We're going to put 0 back into the original function, which was arc cosine of x over 4, but 0 divided by 4 is still just 0. So we're looking for the arc cosine of 0. As a reminder, the ratio goes into an inverse or an arc function, and we're looking for an angle. So what angle gives us a cosine value of 0? And that occurs at pi over 2. Now remember, we also have to stay within the range of our arc cosine function. So from 0 to pi will be the only answers that our arc cosine function gives us. So the inflection point for this function will be 0 pi over 2.